Okay, we are going to start off this week with one more problem in section 3.7. This is on optimization still. Okay, and this is a very final problem on that handout that is posted on Canvas. This is problem 7. A rectangular garden with an area of 30 square meters is surrounded by grass border 1 meter wide on 2 sides and 2 meters wide on the other 2 sides. And we're asked to figure out what dimensions of the garden will minimize the combined area of the garden and the borders. And you have a picture here to help you out. This is the garden, and then it's surrounded by this grass border, and we're told some things about those two areas. Is we know the total area of this, and we know how much wider the total area is of the garden and the grass border. So I'm told the grass border is 1 meter on this side and 2 meters on this side. Okay. So I've already got a picture. I don't need to draw another one. First step I might do is maybe assign some variables to this particular figure. Okay, so I'm asked to figure out what are the dimensions of the garden, so that inside part. So maybe I will call this side X. I'll call this side Y, which means this side is X and this side is Y. Okay. I might also want to know something about this length and this length, because I'm asked what dimensions of the garden will minimize the combined area of the garden and the borders. So I do need to know something about the combined area. The left side, well, let's see. It is X, or excuse me, that's the height. Gotta watch myself there. This length here is this length Y plus another 1 meter on that side and 1 meter on that side. So that length is Y plus 2. And then similarly, this length, well, I have a length of X here, that's what I called it, plus 2 meters plus 2 meters. So that gives me a length of X plus 4 on that side. Okay, so I've labeled my my figure. One other thing I know about it is the area of the garden itself is 30 square meters. I'll just go ahead and note that. Now that I have that, I'm going to move on to step 2. Step 2 is, can I figure out some equations? I need, let's see, I need an equation for the quantity that I want to minimize, and I need a constraint. What do I know about this? Well, first of all, I know that the area of this is 30 meters squared, the area of the garden. So let's see, area is length times width, so X times Y is always equal to 30. I know that is true. So I might call that my constraint. I want to figure out the dimensions of the garden that minimize the combined area of the garden and the borders. So I want to minimize that combined area. So I need to find an equation for the combined area. The combined area is also a rectangle, so I'm going to multiply length by width. That area is, let's see, length. It is X plus 4, we already said that, times width, which is Y plus 2. So this is what I want to optimize. And this is my constraint equation. So I have 2 equations. I can work with those. Now, I'm going to go on to step 3, and I'm going to combine those two equations to form a single equation, to where I have this quantity that I want to optimize as a function of only one variable. Okay. I'm going to write those equations down again. Xy is equal to 30, that's my constraint. A is equal to x plus 4 times y plus 2. Let's maybe make this a function of the variable x, which means I'm going to solve this equation for y and then substitute it into the area equation. Y is equal to 30 divided by x if I divide both sides by x. So if I put that into the area equation, the area becomes x plus 4, that doesn't change, times y, which I know is 30 over x plus 2. Okay. I am going to expand that for the sake of calculus. X times 30x is 30. X times 2 is 2x plus 4 times 30 over x is 120 over x plus 4 times 2 is 8, which is equal to 38 plus 2x plus, I'm going to rewrite this as 120x to the negative 1 power. That is my area function. And note that I have that as a function of only one variable x, so I will notate it as that, just to remind myself. This was step 3. Okay, so I've got that. I am now going to find the domain of that particular equation. Let's see. It looks to me as if the area could technically not necessarily get as large as I want, but the x value can certainly get as large as I want, because as x here gets larger, the width y will get smaller. As x here gets smaller, the width y will get larger, even though they're constrained by this. So the only thing I can really say is x cannot be negative or 0, because then I would not have area. So the domain for this particular equation is 0 to infinity. Now I'm going to use calculus methods to figure out what is the value of x that will minimize the area. A prime of x, the derivative of the area function, equal to the derivative of 38, which is 0, plus 2 times the derivative of x, which is 1, plus 120 times the derivative of x to the negative 1, which is negative x, to the negative 2 power. I'll simplify that and get 2 minus 120 over x squared. Okay. I have a derivative. I need to find critical points. So critical points where that derivative, a prime is equal to 0, for the derivative, a prime does not exist. So, and my derivative is once again 2 minus 120 over x squared. I'm going to figure out what makes that equal to 0. That is where 2 minus 120 over x squared is equal to 0. Add 120 over x squared to 0, or to both sides, excuse me, and I get 2 is equal to 120 over x squared. I'll multiply both sides by x squared. I get 2x squared is equal to 120. Divide both sides by 2. I get that x squared is equal to 60. I'm going to take the square root of both sides of the equation, and I get that x is equal to square root of 60, technically plus or minus square root of 60, which is equal to, if I simplify about plus or minus 7.75. But x is a length. Its domain, or the domain of this particular function is from 0 to infinity. So I'm going to choose the positive. So at square root of 60, I have a potential critical point, or I do have a critical point. I have a potential minimum value. I can note also what values make that derivative not exist, or a prime of x to not exist. This would be where x is equal to 0, but this is not in domain. Not in the domain. So I can disregard that particular critical point. So I only have one point to consider for this particular equation. Now I need to make sure that that particular point gives me a minimum, not a maximum. Okay, so my critical point is again x is equal to the square root of 60, which is about 7.75. I'm going to use first derivative test to figure out whether it is a minimum or not. I'll draw a number line here, 7.75. I'm going to use maybe, I'm going to test x equals 1 on the left, test maybe x equals, say, 10 on the right. Okay. So a prime of 1 is equal to 2 minus 120 over 1 squared, which is equal to negative 118, which is certainly negative. So all I care about is that it's negative. So the function is decreasing. F prime is negative, or a prime, I should say, for that particular interval. I can test the other interval as well. I can say, well, a prime of 10 is equal to 2 minus 120 over 10 squared, which is equal to 2 minus 120 over 100, which is equal to 0.8, which is positive. And all I really care about is that it is a positive value. So it is an increasing function in that interval, which by the first derivative test tells me that this is the value of a, or the location, I should say, of a minimum. A relative minimum happens to mean absolute minimum in the domain in this case. Okay, so now that I have that, I can say what the dimensions of this particular garden are. Okay, so the garden dimensions, I now have the x value, so I know what the length of the garden is. X is equal to the square root of 60, which again is about 7.75 feet, which means that y is equal to, we said it's 30 over x, which in this case is 30 over the square root of 60, which is equal to the square root of 15 if you do a little simplification. Square root of 15. Okay. And I will not find the approximation for that, because my guess would be that you know how to find that in your calculator. And that is all for this problem. We now know the dimensions of the garden that will give us the minimum combined area of the garden and the borders.